In this video, we're going to look at how to add, subtract vectors. We're going to look at how to take a scalar multiple, and we're going to look at dot products. I'll start with adding and subtracting vectors. It's very important when we're adding and subtracting vectors, we can only add and subtract like terms. So let's start by defining two vectors. Vector v equals ai hat plus bj hat. Vector w equals ci hat plus dj hat. Remember that arrows above the vector names always indicate a vector, so it does not matter what I call them. I called them v and w here. So if I want to add or subtract these two vectors, I'm going to look at v plus minus w hat, plus minus just indicating that I can do either. So to do that, I'm going to take their horizontal components, a and c, add those together. I'm also going to take their two vertical components, the b and the d, and I'm going to add those together. So let me take an example. Let's let our vectors v and w be defined as v equals 2i hat plus, let's choose a 5j hat. And for w, I'm going to make w negative I hat plus 3j hat. Remember, negative I just meaning a negative 1. And let's start by finding the sum of these two vectors. So I'm going to look at v hat plus w hat. Well, what that means is I'm going to be taking these two vectors as defined above, and I'm going to add them together. I'm going to add their components together. So I have the 2 plus the negative 1, or 2 minus 1, and that is our I component, or the horizontal component. So I'm going to put my I hat there. And then I'm going to take my two vertical components, the 5 and the 3, I'm going to add those together. And then I place my j hat with those because that is my vertical component. We know that 2 minus 1, let me fix that. That should be my j hat. I know that 2 minus 1 will give me just a 1 I hat. I can write the 1 I hat, or I can just put the I hat there, because anytime we have just that I hat, we know it has a coefficient of 1. And then 5 plus 3 will give me an 8 j hat. Need the hat on my j. So 8 j hat. Our answer should be I hat plus 8 j hat, like so. Let's say we want to do this all over again, but this time I'm going to subtract the two vectors. We'll take vector v and subtract off vector w. So let me change my symbol in between, make that a minus. And all that means is I'm going to be taking these numbers and subtracting instead of adding. So we'll have 2 minus a negative 1. We know that'll turn into a positive, but I'll leave it 2 minus negative 1 for right now. And then we'll take our j components, our vertical components, subtract those, 5 minus 3. 2 minus a negative 1 will give us a 3, or 2 minus a negative 1 will give us a 3. And then 5 minus 3 will give us a 2 j hat. Alright, this time we're going to look at something called scalar multiplication. Scalar multiplication, we're going to distribute the scalar across all the components of the vector. So let's find c times vector v. And vector v we defined as a I hat plus b j hat. So what I might be doing is taking that vector, and I might be distributing my c across it. So c a hat, c times a times my I hat plus cb times the j hat. So let's take an example. Let's find 3 times vector v. So what that means is I might be taking my 3 and multiplying it to vector v. Let me put this down, 3 times my vector. So when I distribute, 3 times 2i is going to give me 6 I hat. And then when I take my 3 and distribute it to the vertical component, I get 15 j hat. Just distributing that term across. We don't need like terms. We know that anytime we have multiplication, we don't multiply just like terms, we multiply across the whole expression. So we're just distributing this, we get 6i hat plus 15 j hat. Let's move on to our last topic, the dot product. The dot product gives us the sum of the product of corresponding components of two vectors. So let's define vector v as ai hat plus bj hat. W is equal to ci hat plus dj hat. Well, v times w then is going to be equal to a times c. We're multiplying the two horizontal components together, plus the two vertical components, the b and the d, we're going to multiply those together. Notice that when we're multiplying these, we drop the I and the j. I'm not including the components anymore because I'm simply multiplying the products, and it becomes a scalar. When I multiply these two vectors together using a dot product, it becomes a scalar. Now, there are actually two different ways of doing vector multiplication. We're working with the dot product. But if instead of seeing that dot, you saw a cross, that is what is called a cross product. So to write that out, you'd see vector v cross vector w, and that is indicating a cross product. We're not going to look at that in this video. We are going to concentrate solely on that dot product. So let me take those off of there. And let's take an example. Let's take these two vectors from what we had before, same two vectors, and I'm going to find their dot product. So we'll take the v dot w, this thing right here. So what that means I need to be doing, I need to look at the horizontal components. My horizontal components, I have the 2 and the -1, so I'm going to multiply 2 times -1. And I'm going to add that to, I need to multiply the two vertical components. That would be my 5 and my 3, so 5 times 3. And once I get that in there, 5 times 3. 5 times 3. Well, we know that 2 times a -1 is a -2. And we know that 3 times 5 is 15, so -2 and 15 give me 13. We've taken the two horizontal components, we multiplied those together. We took the two vertical components, we multiplied those two together as well. Now, just like I discussed before, anytime we are finding a dot product, we will always be left with two scalars. Dot product, we start with the pair of vectors. We are left with, just a single scalar. We are left with a scalar term. Dot product always yields a scalar. Now, we've just completed the sum and difference, the scalar product and the dot product of two vectors with two components. It is important to note that we could do this with any number of components. We could have a three-dimensional space, we could have some sort of z component or third dimension, could have any number of dimensions, and it will always work the same.